So this is diagram, vector diagram for magnetic moments. Okay, we know this is orbital magnetic moment. This is spin magnetic moment. They have resulted. Okay, so why we are showing these two separate? Because we know mu L and mu S. This is about this mu J. Okay, they are opposite direction. We know this is orbital regular or orbital angular momentum vector S. Sorry, spin angular momentum vector S. Orbital angular momentum vector L, their resultant. So in opposite side we got their magnetic moments. Okay, this is not in the same direction as mu J, their resultant of these two, because we know this mu L, mu S. If you take this ratio, the magnetic moments and the mechanical moments. Okay, so their ratio is not equal. Okay. You can see the ratio is not equal, so we get this vector here. Okay, so their ratio is not equal, so this is not directed along as the same direction as mu J. So we can see here this mu L, mu S, magnetic moment, spin magnetic moment, orbital magnetic moment. The resultant mu Ls is not directed along mu J because we have difference in this ratio mu L by PL. Mu S by PS. So here magnetic moments, mechanical moments, their ratio is not same. So we can see in this vector diagram, the resultant is mu Ls, but it is not directed along mu J, which is opposite to the J. Okay, so this is not directed along mu J. Why it is different? Because we have the different ratio. Now we have to calculate the value of mu J, that is resultant magnetic moment of the atom. Now here we can see these two vectors precessing about J. Here these two vectors precessing about mu J. Now we will consider these two only, okay, not this. So here we can resolve these two. Okay, we are calculating the value of mu J. So we have to take help of these two. Now we can resolve this into its rectangular component. Okay, here see. Now what happens to these components? Let's take first mu L. So that will be the theta. Okay, now the perpendicular component to this mu L or the mu J. Okay, so this direction, this is perpendicular. So this perpendicular vector, the component, the rectangular component will get cancelled because this is precession. Okay, we know this is precession. So if this vector will change its direction, and as it is changing its direction, this vector will cancel out with this one. So like this, we will cancel this component. Okay. Now we just have to consider this parallel component because it is contributing to the total magnetic moment. Why? Because it is in same direction as mu J. It is not changing its direction, so we just have to take this one. Okay, it is contributing, not this one, because it is cancelling with its counterpart. So we just have to calculate this one. So what will be the value of this parallel component to the mu J of mu L? We know we can calculate it like this. So mu L and its contributing part, that is cos L J. Is it right? So this component is nothing but this one. Okay. Now we have to do same for the mu S. We know this cos Lj angle with cos angle between L and J. Okay. Here L and J. This one is between S and J. So we know mu J is the vector component of mu L and cos Lj plus the vector component of mu S and angle between S and J. So here we can put the value of mu L and mu S, which is nothing but what is the value for mu L? Particular value Phy 4 pi m. The value of mu is s 2s eh by 4 pi m. So by putting these two values in this equation, we get eh by 4 pi m in bracket L cos Lj plus S cos Sj. Cos Lj, we know it as S square plus J square minus, okay, so S square plus S square minus S square by 2 Lj. Similarly, the value of cos Sj is S square plus J square minus S square by 2Sj. So by putting these two values in this equation, we get the final, and we write it directly, mu J is nothing but Eh by 4 pi m into J into 1 plus J square plus S square minus S square by 2J square. So we know in Zeeman effect, that is weak magnetic field effect, the spectral lines split, okay, and the strong magnetic field effect, which is nothing but partial line effect. There, the partial line effect, the coupling between L and S is broken, okay, and in Zeeman effect it is not broken. So we get the resultant J which precesses above around H, that is applied magnetic field, weak magnetic field. So this is Zeeman effect. Now we can show the change in energy of the atom during this application of weak magnetic field. B is nothing but, we will use this mu J, that is total magnetic moment, okay, and H cos JH. We know if J precesses around H, we give the energy like this, okay, their precession, okay. So this is energy of that atom. Now we know that J precesses around H, it has special concentration, okay? That means, so this is J, it has special concentration, that means it has certain values, certain orientations only to revolve around this, okay. That means these are the discrete orientations. So what will be the values? That I will represent those orientations with Mj. So Mj is nothing but magnetic quantum number. That means when J has some values, some orientation, some ways, okay, that possible ways to revolve around this H are nothing but Mj. We know this, okay. So we can correlate it here. So this is total magnetic quantum number Mj, which is nothing but the possible orientations, allowed orientations of this J around this H, okay, these precessing paths we can say, okay. So these orientations are nothing but the values of Mj, and we know the values of Mj from varies from 2J plus 1 to minus of 2J plus 1. So this will be the possible values for this total magnetic quantum number. Now we have the relation for Mj and H as Mj is nothing but J cos J. Okay. So this relation we can put as cos JH Mj by J. So this value of cos J we can put it here. So what is the equation? Equation will be T is equal to mu J dot H dot Mj by J. Now here we have the value for mu J. Okay, this mu J. So this value we will put into this equation. So what will be the resultant equation? So it will be D, just put this value into this resultant equation, mu J is value, okay? So TH by 4 pi m, and obviously J is J, then H, then mj by j, and then lastly take this one, L square by 2j square. So while we are doing this, we are finding the interaction energy. So this D, which is nothing but interaction energy, we know is 4pH by 4 pi m into H. This J and J cancels, so mj and G. This is landing G factor, which is nothing but splitting factor. Okay. This interaction energy we can represent in wave numbers as term shift. Okay, so D by Hc. So this is interaction energy in wave numbers, nothing but term shift. So using the value of D and this Hc, we know we will just write 4 pi mc into mg into g. Okay, so that will be del T. Now here this TH by 4 pi mc is nothing but Lorentz image. So Lorentz image capital L. So the resultant term shift, the interaction energy will be, we can put the value of L. Okay, for like so this will be the interaction energy, the change in energy level. If you calculate for each mj, okay, for each mj you will get the values. So these will be the interaction energy. If you calculate, so this is term shift, interaction energy, change in energy level when we place an atom in a weak magnetic field, which is nothing but Zeeman effect. So that change in energy of atom or energy, each energy level, you can calculate using this mj. So this is nothing but interaction energy or change in energy, term shift. So consider this spectrum diagram of sodium atom. Okay, so these two lines are showing sodium D lines within no magnetic field. Okay, the magnetic field is not applied here. We have applied the weak magnetic field. Okay, so these two original lines without magnetic field, in a weak magnetic field, they get split. The first line, that is D1, sodium D1 D line, it is split into four components. Okay, four lines, and that second one D2 is split into 6 components. So this happens. This is what happens in anomalous Zeeman effect in a weak magnetic field. Okay, so this is when we do not apply any magnetic field to the D lines, sodium D lines. So these are just singlets or single lines. When we apply the weak magnetic field, they get split. Okay, so first line is split into 4 lines, and the second one D2 line is split into 6 components. Okay, so here this splitting from the hypothetical center of gravity, that is first, second. So this energy difference is calculated using G mj into L, but we are taking it in terms of Lorentz unit. So we don't have to write the capital L. We are representing this energy term, energy difference, interaction energy in terms of Lorentz unit. So we don't have to use that capital L. We will just write the landing G factor and total quantum number mj. So using this, we will take an example to calculate this one. Okay, so Using this formula, we can calculate the energy difference between these lines. So this is how they are splitted when we apply weak magnetic field. Now, there is a selection rule. Selection rule of del Mj 0, del Mj plus or minus 1. So these are the two selection rules for these transitions. If the transition obeys this selection rule, then it is not denoted by the pi symbol, and if this transition obeys this transition rule, then that line is represented by sigma. Okay, so these are. So let's take how this line, this 3s1/2 line, splits into two components and calculate their mj values. Okay, mjg values. Okay, so let's take this line here. So for 3s1/2, we will have the value of L0 as it is S as the value half, obviously J will have the value half. Now we can calculate, we need mjg. So we have G as 1 plus K square plus S square minus L square by 2H. So if we calculate this, we will get value of G as putting the value of J plus 1, S plus 1, we know this. So just put these values and calculate these values, we will get 2. So landed G factor for this line is 2. We have to calculate Mj, we have the value for J. So obviously Mj will have the values 1/2 minus 1/2. So the resultant value for mjg will be we got value G, value of J is 2, so Mj is this, so mjg will have the two values. From here we can see 1 and minus 1. So this is nothing but minus 1, 1. Similarly, we can calculate other values. Here it will be 1/3, minus 1/3. For this one, we will have 2, 2/3, minus 2/3, and 2, okay, minus 2. So this will be the values of mjg if you calculate using G factor. So we know landed G factor as 1 plus K square plus S square minus L square by 2J. So this G, this landed splitting factor, is main cause for Zeeman effect to split the spectral lines into more complex form, because in Zeeman effect, in anomalous Zeeman effect, we consider this S. We consider the speed, okay, not only the orbital motion of electron. So when we consider S, the G comes in part, okay. So here you can see, if we cancel out S, if we take S as 0, then this quantity will be 0 and G will have the value 1. So it is not taking any part in any equation, any splitting, any energy, interaction energy. So to anomalous Zeeman effect, to explain anomalous Zeeman effect, we need this G factor, this splitting factor. Otherwise, it will have the value 1. So obviously, this only the orbital angular momentum we will take into account. So this is main cause for Zeeman effect, anomalous Zeeman effect. Otherwise, it is normal Zeeman effect. Okay.